Welcome to lecture 25 of electromagnetic field and waves. Um, like always, we'll start off with a brief review of where we left off last time, and then we'll take it from there. So last time we basically introduced phasor notation. And the idea with phasor notation basically was that we make all the time dependence implicit. So for example, the time dependent complex voltage V of Zt would be the phasor voltage, which is we represent it as Vp e to the I omega t, right? And the phasor voltage basically had all the it had the complex amplitude, and it had all the z dependence inside of it. The second thing that we started to do was that we looked at a lossy transmission line. Now, a transmission line, as we said, is just it's an element which transfers electromagnetic energy from one place to another, and we are modeling it as two conductors. So our model for a lossy transmission line was the following. Let's say these are some terminals, and we have a resistor per unit length, we have an inductor, then we had a node, we had a transconductance, we had a parallel capacitance, and this was connected to the second terminal. And then similarly, in another segment of delta Z, you had another resistor, another capacitor, another transconductance, capacitance, and once again in another section of delta Z, resistor, inductor, transconductance, capacitance, so on and so forth, right? So this was our model for a lossy transmission line. The distance between here and here, this distance we call delta Z. So we took a small segment of a very long transmission line, and so we said that this transmission line can have a resistance R per unit length, an inductance L per unit length, a transconductance G per unit length, and a capacitance C per unit length. So this resistor in a segment of length delta Z was R delta Z, this inductance was L delta Z, this transconductance was G delta Z, and this capacitance was C delta Z. And same for all of the other elements. I'll just quickly label them so that we have a reference for the rest of this lecture. Now the thing about the transconductance is that the transconductance allows parasitic flow from this terminal to this terminal. If there is no transconductance, then you don't have shunting of your signal. And furthermore, what we did was that we labeled our nodes. So we called this node 1, we called this node 2, and we had called this node 3. We had called the voltage at node 1 V, we had called the voltage at node 2 V plus delta V, and the voltage at node 3 as V plus 2 delta Z. We had called the current leaving node 1 I, we had called the current leaving node 2 as I plus delta I, and we had called the current leaving node 3 as I plus 2 delta I. And this current we had called minus delta I, and this current was the same, minus delta I, right? So this was our model for a transmission line, which is just two parallel conductors transporting electrical energy or electrical signals, right? Using this, we derived the telegrapher's equations for a lossy transmission line and the telegraph equations were that so we had dv of z by dz is equal to minus, we had a lumped label x I of z, and the second telegraphic equation that we had was, let's just call this equation 1. Let's just use a numeric 1. And the second telegraphic equation was that di of z of dz is equal to minus y v of z. So the telegraphic equations for transmission lines. Remember, we did telegraphic equations for electric and magnetic fields also when we're doing Maxwell equations and electromagnetism. And these are also telegraphic equations, and they link the voltage and the current. So they're coupled first order differential equations, right? How do we derive them? Well, we apply the Kirchhoff's current law and the Kirchhoff's voltage law on the transmission line model you saw before, and we did this for a lossless line, we did this for a lossy line last time, and and these are these equations in phasor form, of course, right? So you solve the phasor form and you just multiply by e to the power iota omega t to get the time dependence. And these factors of x, so this x was a lump parameter which was iota omega L plus R, and y was equal to iota omega C plus G. Using these and substituting one into the other, we were able to derive the wave equations for lossy transmission lines. And the wave equations that we derived were that so del 2v by dz square was equal to x y times v, and the second wave equation we had was del 2I by partial z squared was equal to x y times I, right? And then what we did last time at the very end was that we substituted a parameter gamma squared, which we called was equal to xy. So if you do that, your final wave equations become del 2v by partial z squared minus gamma squared v becomes equal to 0, and the other wave equation becomes del 2I by partial z squared minus gamma squared I is equal to 0. And of course these are also in phasor form, because it's easy to write these equations in phasor form. If you were doing everything in time domain, you would have partial t square terms also, and these would just be harder. And we will call this equation 3 if we ever need to recall it, and you will call this equation 4, and these are the wave equations. So this is where we left it off last time, and the first new thing that we will do today is that we will write down the solutions to these wave equations. So so the general solutions for v and I, these are just second order homogeneous differential equations, right? So the general solutions would be that in general v of z would be equal to some v plus e to the minus gamma z plus v minus e to the plus gamma z, right? Where this is the component that propagates in the positive z direction, and this is the component that propagates in the negative z direction. And we had a detailed discussion about this last time also, okay, why that is. And similarly, the current is also a second order linear homogeneous differential equation. So in general, the solution to the current in general would also be some I forward propagating e to the minus gamma z plus some I negative e to the plus gamma z. Now, this factor of gamma is of course factor of gamma squared is of course so gamma squared is xy, so gamma is equal to the square root of x into y, so this is equal to the square root of iota omega L plus R into iota omega C plus G, and this is in general a complex quantity. Right? So the propagation constant is a complex quantity. Okay, so now, I mean, even if this is a lossless, even if this was a lossless waveguide, then R and G would be 0. Then you would have square root of minus omega square LC. So gamma would still be complex. So in general, it is complex for both the lossless and a lossy waveguide in the way that we define it here. So we can express this. So we can express capital gamma as gamma prime, which is the real part, plus iota gamma double prime, right? So gamma prime is the real part, and this is the complex part. So we can write V of z as being equal to V plus e to the minus gamma prime z multiplied by okay, let's just write it in expanded form, minus iota gamma double prime times z plus V minus e to the gamma prime z plus iota gamma double prime z, right? Now, in general, we know that we are working in phasors. We are working in phasor form. So we know that in reality, V plus or minus is equal to the mod of V plus minus times e to the I phi plus minus, right? So if we convert back to time domain, then V of zt in time domain would be equal to V of z omega, which we found here. Yeah, first I'm just write it as V of z times e to the iota omega t. Okay. So that's, and the physical voltage, the physical time dependent voltage in this transmission line this will be so this will be equal to, so the physical voltage, so let's just say V physical as a function of zt be equal to the real part of the complex voltage, right? And that'll just be equal to the magnitude of V plus times e to the minus gamma prime z cosine of omega t minus gamma double prime z plus phi plus, and you will add to this v minus e to the gamma prime z cosine of omega t plus gamma double prime z plus phi minus bracket close. Okay, so that's the real part, and I hope that makes sense. So the first term, I think I should just write it down again. So the first term, which was the magnitude of V plus e to the minus gamma prime z cosine of omega t minus gamma double prime z plus phi plus. So this is the first term. So this term is in fact, so it's a decaying, because you see this factor, this is decay because it's a negative exponential. So this is a decaying wave that is propagating to the right. And by the exact same logic, the second term corresponds to a decaying wave propagating to the left. So now in a lossless transmission line, now in a lossless transmission line, R is equal to G is equal to 0. So in a lossless transmission line, a factor of gamma becomes equal to the square root of iota omega L plus 0 times iota omega C plus 0. So it becomes equal to square root of minus omega square LC. That becomes equal to iota omega square root of LC, right? So that's equal to 0 plus iota gamma double prime, because the real part is 0, is purely complex. So what this means is gamma prime is 0 for a lossless transmission line. Right? And that makes sense, because in a lossless transmission line, your voltage should not be decaying, right? As it passes through this this transmission line. So if that's good, then once again we are now in position. Finally, we can now find the characteristic impedance. And this is where things start to get interesting. So as always, we define the characteristic impedance using the symbol Z0. So we'll do that. So Z0. The characteristic impedance is the ratio of the voltage at that point to the current at that point. So let's find the characteristic impedance for the forward propagating wave, which is V plus over I plus. So so for the right traveling decaying wave, so for the right traveling decaying wave, V of z becomes equal to V plus e to the minus gamma prime z times cosine of omega t minus gamma double prime z plus phi plus, right? This is what the voltage is. Now, using the telegraph as equation, so using equation 2, which was the let's just use the equation, this one, di by dz is equal to minus y times v. So if we use this equation, then what we find is that so for this v of z, for the right traveling v of z, the current I plus becomes equal to y, which is just from the telegrapher's equation, over gamma. This is the factor that comes because of the integration, times v plus e to the minus gamma prime z multiplied by e to the minus gamma double prime I times z, right? So that's the current. So the characteristic impedance z naught becomes equal to v plus over I plus, and that becomes equal to gamma over y, which becomes equal to the square root of xy over y, which becomes equal to the square root of x over y. Now we know what x is and we know what y is. So z naught becomes equal to, and this is a very important result, becomes equal to the this is perhaps one of the most important results, one of the most, not the most, in transmission line theory that we will study. So z naught becomes equal to I omega L plus R over iota omega C plus G. Okay, and this is so important, in fact we'll make a box around it. And this is the relation for the characteristic impedance. So the characteristic impedance of the of a lossy transmission line at any point along the line is square root of iota omega L plus R divided by iota omega C plus R. So z naught is complex in general, right? And if R is equal to G is equal to 0, which means you have a lossless transmission line, then only z naught becomes equal to the square root of L over C, which is what we had before. Right. So this is the impedance at every point, right? So this factor, square root of iota omega L plus R over iota omega C plus G, this is the impedance, the characteristic impedance of the transmission line. at every point, looking towards the right, and you will find the same characteristic impedance looking towards the left, right? um, so I hope we understand the concept of characteristic impedance. And how we've derived it, because we'll need it from now on. So of course, now the thing is that the purpose of a transmission line is to carry energy and signals. So what we'll do now is that we'll go into our next topic, which is that now, from now on, so we've considered transmission and we've calculated its characteristic impedance. Now what we want to do is that we want to consider a terminated transmission line. Right, we want to consider a terminated transmission line. So what we'll do is that we will add a load impedance ZL at the end of the transmission line. So let's just sketch this new terminated transmission line that we're talking about. So the idea basically is that this is your transmission line. This is one conductor, and this is your second conductor, and both conductors are connected on the terminal end, so they're terminated in what we call a load, right? So for example, if the transmission line coming from your local electricity supply company terminates at an air conditioner in your home, so ZL would be your air conditioner, right? Or if it's a fan or a light or a washing machine or whatever. And so this is a terminated waveguide, and now I want to connect this to what we've done before. So we have done reflections of electromagnetic waves in dielectric and conducting interfaces. And we saw that we always get reflections across interfaces, right? And we derived the Fresnel equations and so on and so forth. And we looked at concepts such as skin depth in a conductor. So for a transmission line, as shown above, so for a terminated transmission line such as this, so it's very fair to assume that some of the right traveling wave will be reflected to the left. Right? So at any point, so at every point, the total voltage, the wave will be a superposition of left and right traveling waves. Um, so this is our transmission line. This is our load. Right? And we assume that there is some right traveling wave v plus of z, there is some left traveling wave v minus of z. We call this point where the load is, we'll call this z is equal to 0. Taking everything to the left will be negative. And we will assume we will take a lossy transmission line. Right? We will take a lossy transmission line. So at every point, then v of z becomes equal to a superposition of v plus of z plus v minus of z, right? The forward and backwards traveling waves. So v of z becomes equal to some amplitude a plus, which is the amplitude of v plus of z, times e to the minus gamma z, where gamma is a propagation constant, plus a minus e to the plus gamma z, right? Where that's v of z. Now what we're doing here, the idea basically is that now v plus of z, which is the right traveling wave, is the input wave, let's say from the source, right? So for example, a signal generator. Such as the ones you had in your freshman physics lab. So v plus of z is the input wave from a source, and v minus of z is the reflection of v plus of z. So their amplitudes are related at z is equal to 0, right? And so what we'll say is that so at z is equal to 0, the amplitude of the left propagating wave will be equal to some factor capital gamma L times v plus at z is equal to 0. Okay, and this is what we will call the reflection coefficient. The reflection coefficient at the load at z is equal to 0. Okay, so then what this implies is that so a minus becomes equal to gamma L a plus, right? So the reflection coefficient tells us that at z is equal to 0, what is the amplitude of the reflected wave. So then v of z becomes equal to a plus e to the minus gamma z plus gamma L A plus e to the gamma z, right? So this becomes equal to a plus whole into e to the minus gamma z plus gamma L e to the gamma z. Okay, and we will call this equation A. Okay, now that's the voltage, that's the total voltage. So this is net voltage or total voltage at load. It's a superposition, right? Actually this is called the total voltage. Now for the load we'll have to plug in z is equal to 0. It's a total voltage. Now the corresponding current can be found using the telegrapher's equation. So the corresponding current can be found using equation 1, right? So we have the voltage now, which is a superposition of a right and left traveling wave, and we want the current. So we'll find the current using our telegrapher equation. So we'll use our telegrapher equation, and so the telegrapher equation is just that I of z is equal to minus 1 over x dv by dz, where x is equal to iota omega L plus r, right? And gamma is equal to square root of xy, which is equal to the square root of iota omega L plus r times iota omega c plus g. So I becomes equal to minus 1 over x partial dv by dz. So I then becomes equal to a plus gamma over x times e to the minus gamma z minus capital gamma L e to the gamma z. Okay, so now we know that x is iota omega L plus r, gamma is square root of xy, so that's that. So this ratio, so that's what I is. So I becomes equal to I of z becomes equal to the square root of y over x a plus times e to the minus gamma z minus capital gamma L e to the positive gamma z, right? Now if you recall, if you recall, that the characteristic impedance of a lossy transmission line Z0 was equal to the square root of x over y, right? This is what we derived a few slides ago. So I of z becomes equal to a plus over Z0 times e to the minus gamma z minus gamma L e to the positive gamma z. Now just to repeat, we are now doing a terminated current line, a terminated transmission line. Before this, we were looking at current and voltage at every point in an infinite transmission line, right? So now what we have is that we have So we now have current and voltage in a terminated transmission line. Right? So and this factor gamma L was the reflection coefficient at z is equal to 0. And of course reflections are taking place at the load. Right, reflections are taking place at the load, but we can actually define, it might be a useful quantity, we can define a more general reflection coefficient right. We can define a more general reflection coefficient, and we can just call this capital gamma of z, where capital gamma of z is just the ratio of the right traveling wave and the left traveling wave, and so this is equal to the ratio of the left traveling wave, which is v minus of z, over the amplitude of the right traveling wave. Right, so we can define a general reflection coefficient, and this general reflection coefficient at every point z becomes equal to v minus is just a minus e to the gamma z over a plus e to the minus gamma z. So this becomes equal to, now we know that a minus over a plus is just equal to capital gamma L, which is the reflection at the load, times e to the 2 gamma z, right? And of course the general gamma at z is equal to 0 must be equal to gamma, let me just draw this properly for you, gamma L, because by definition that's what it is, right? Okay, so we can also define a general reflection coefficient. So now we have the current and we have the voltage. Now by definition, at the position of the load, right, the impedance of the load must satisfy the following relation, right? The impedance of the load ZL must be equal to the total voltage at Z is equal to 0 divided by total current at Z is equal to 0, right? So now if we substitute equation A and equation B, where equation A is our expression for the voltage at any point and at a general point, and expression B is our expression for the current, right? Now if we substitute that here, then ZL becomes equal to so this becomes equal to A plus, which is the amplitude of the forward propagating wave, times 1 plus gamma L over A plus over Z naught, where Z naught is the characteristic impedance of the transmission line, times 1 minus gamma L, right? So this becomes equal to Z naught times 1 plus gamma L over 1 minus gamma L, right? So the load impedance must satisfy ZL is equal to Z naught times 1 plus the reflection coefficient over 1 minus the reflection coefficient. So you can use this to find an unknown impedance if you know the reflection. So you can imagine that if I give you some complex component which has some inductance, capacitance or resistance, but I don't know what the impedance is, if you have a transmission line for which you know the characteristic impedance and you connect it to your unknown load, then by monitoring the reflection coefficient, you can actually find what the load impedance is, right? So that's one use of this. So it's sort of like making an impedance analyzer using a transmission line. The other thing we can do is that we can solve for the reflection coefficient at the load. We can solve for ZL. We can solve for gamma L, and what you find is that, so if you multiply both sides, what you find is that, so ZL minus ZL gamma L becomes equal to Z naught plus Z naught times gamma L. So if you just rearrange terms, so Z naught gamma L plus ZL gamma L becomes equal to ZL minus Z naught. So if we just make gamma L the substitute of the formula, so then gamma L, which is the reflection coefficient at the load, becomes equal to a very nice expression, which is that it becomes equal to ZL minus Z naught over ZL plus Z naught. Okay, and this is a very, very important relation. Okay, and we'll call this equation C, and this tells us that given a transmission line and given a load, how much of the signal is deflected, right? Because notice that if ZL becomes equal to Z naught, then this factor gamma L becomes equal to 0. So no reflections. So the right traveling wave will not be reflected. Right? And we get perfect coupling, signal delivery. Now what this is called, so this is called a matched load, right? And the act of matching the impedance of your transmission line with the impedance of your load, this is called impedance matching. Now, oftentimes, when you have, let's say you have a coaxial cable, typically you use a lot of coaxial cables in laboratories, and a lot of times when you buy a cable, the manufacturer tells you the impedance of your cable. It's, let's say, 50 ohms or whatever, and the reason it gives you the impedance is that you want to match the impedance of your coaxial cable with the output impedance of, let's say, your function generator, and you want to match it with the input impedance of your oscilloscope. Basically saying is that if, let's say, this box is a signal generator and this is a coaxial cable, this is a transmission line, and this, let's say, is an oscilloscope. So for perfect transmission, you want to match the output impedance of this is the source, with the characteristic impedance of this, with the load impedance of this. If you can do that, then you will have perfect transmission between the signal generator, the transmission line, and the oscilloscope. If you can't do that, then you get some parasitic reflections, and then you can't have perfect delivery of your signal. Now, this factor of gamma L is obviously equal to V minus of Z over V plus of Z, right? At Z is equal to 0. So this becomes equal to, we've seen, ZL minus Z0 over ZL plus Z0. Now, in general, ZL and Z0, these are complex numbers. So in general, capital gamma L is a complex quantity with a magnitude and some phase, right? So this is, in general, this is a complex number in general, which means that there can and will be a change in both the amplitude and phase of the reflected wave compared to the incident wave. Right? I mean, when we were doing Fresnel equations, and if you remember when we were doing electromagnetic waves, we saw that there is always a phase between the reflected and incident electromagnetic waves, and we saw that for perfect reflection, that phase was equal to pi between the reflected and the incoming wave, right? Similarly, in transmission lines also, you can have a phase relationship between the reflected and the incoming light, and that phase depends on the characteristic impedance Z0 and the load impedance ZL. Now notice that, right? So I hope this is conceptually clear. So now notice that VL, which is the voltage at the load, this is the voltage at the load, VL is equal to V plus V minus, right? Which is equal to V plus gamma L V plus, right? By definition. So we can also define something called the transmission coefficient. So we can define the transmission coefficient as, so we can call it tau, and tau can be equal to VL, the voltage at the load, over V plus, right? So this gives you the ratio of the voltage at the load, which is transmitted to the load, over the incoming incident voltage, and this transmission coefficient becomes equal to 2ZL over ZL plus Z naught, right? And this transmission coefficient in general is also a complex number, so we can write it as tau e to the some I phi, right? So this is the transmission coefficient. And the reason that I highlight this is because notice that if gamma L is real and positive, which it very well can be in a lot of cases, then tau can actually be greater than 1. So the voltage at the load, which is a superposition of V plus and V minus, can be higher than V plus. Now you might say that this is a problem. I mean, are we violating the principle of conservation of energy? But the thing is, we're not, because the reason we're not, but current will be lower, such that average power dissipated at load, dissipated, we can actually use the word transmitted to load, will be less than or equal to the incident power, right? So this will hold. So all in all, the most important concepts of this lecture, the readings for this lecture are still chapter 10, further sections of chapter 10 in Hyatt, engineering electromagnetics. The main takeaway things that I want you to take away from this lecture are the telegrapher equations for a lossy transmission lines, the wave equations for a lossy transmission line, how did we get there, the use of phasor notation. I further want you to actually let me just write this down just to make sure you understand this. So telegraphers and wave equations for lossy transmission lines, right? The use of phasor notation. Almost everything we did in this lecture was phasor notation. Calculate terminated transmission lines, finding the reflection coefficient, and the concept of impedance matching. And its importance, right? So I hope that's clear. Next time what we'll do is that we'll take this a bit further. We will look at the amount of power that's transmitted, and we will look at how standing waves form in transmission lines. And then we'll do some more selected topics from transmission lines, and then we'll basically conclude how much we wanted to discuss in this course. Thank you very much for listening. And of course, this is chapter 10, height, right? That's your reading, and I'll upload these lecture notes on LMS also. Thank you very much.